Okay, so we can start the second half of this afternoon with two talks in English. And the first one is by Professor Achille Varzi. It's a very great honor and a great pleasure for me to introduce Professor Varzi, who is undeniably one of the 2 or 3 most important authors internationally on the topics of mereology and metaphysics of composition. So it's really a great honor to have him here for this conference. Professor Varzi is a professor of philosophy at Columbia University in New York, where he has taught since 1995. And besides writing one of the most important books in mereology, which is called Parts and Places, together with his co-author Roberto Casati, he has also written several books in English, in Italian, and even in French. French-speaking people here are certainly aware of the book Ontologie, published by Itac, and so in many areas of metaphysics, he has written innumerable papers and books. And before writing about a book on parts, he has written another important book on wholes, but not the kinds of wholes that are relevant to mereology, but the kind of whole which we could call the donut sense of whole. And so today he's going to present he's presenting a talk entitled On Being Ultimately Composed of Simples.
Thank you, Jean-Baptiste, and thank you all. Many thanks to Claudine for the invitation. It's an honor and a pleasure to be here. And thank you also for this very kind introduction. The topic of my presentation is, in fact, theories of parts and whole theories of composition in some limited contemporary sense, the one that goes with mereology, even though the general issue in the background has a very long history, and it goes back all the way to the pre-Socratics. By way of introduction, let me go very briefly to what I wrote in my abstract. So I'll try to, for one, stick to what I promised. So here's one good thing about mereology as we understand it today as a theory of the parthood relation, that at least the standard ways of formulating such a theory, the classical one, or its variants, is in principle neutral with respect to the question of atomism. That means that the theory admits of various sorts of models. Some of them are atomistic models, i.e. models in which everything is ultimately composed of atoms, i.e. simples. These two terms will be used as having the same meaning. But it also admits of models in which everything is divisible into parts, which in turn have parts, which in terms have parts, and so on. In other words, models in which everything is made of atomless gunk. The word gunk, as I'm sure you know, is one of David Lewis's inventions. It's not particularly nice, but it now has a technical meaning, so I'll be using it with that meaning. So that's a nice thing, because there is a general worry about the neutrality of mereology with respect to metaphysical issues, or to put it in terms of a hope rather than a worry. There's just a hope that one might identify a general skeleton of the theory which is metaphysically and ontologically neutral, a piece of formal ontology in Husserl's sense of formal. And then, of course, you may want to enrich your theory by adding specific principles which are the expression of specific metaphysical views. For example, you may or may not be an extensionalist, i.e. you may or may not believe that there are no distinct entities that are composed of the same proper parts. Depending on that, you will or will not have the relevant principle. You may or may not believe in unrestricted composition, and then that's obviously a substantive principle. But the idea is that there must be some general skeleton which is neutral. Well, surely the question of atomism doesn't belong to that skeleton. It is like extensionality or unrestricted composition, a substantive view. So that's the standard wisdom, that if we have views on such matters, particularly now atomism versus atomlessness, then we must rule out the unintended models which are otherwise admitted by the theory. And we do so by adding specific axioms that select, that restrict the number of models. We know that if these are first-order theories, then we're doomed to fail for a number of interesting metalogical results. Say the Löwenheim-Skolem theorem by itself is going to make it very difficult to rule out models that we don't like. Then there are isomorphisms, unintended models, and so on. But still, when we try to formulate our views, that's how we do it. We just add axioms and we try to at least convey the intended models that we have in mind. Well, what I want to do today briefly is to show that this is a little more difficult than the general idea that I've just described might suggest. It's less straightforward and in fact more problematic. So in a way, this would be a better title. This is from a gas station in Nebraska. You might be familiar with this, which has become a joke. Don't trust atoms, they make up everything, which is appropriate today in the United States. All right, so let me start simply by defining a few basic terms. The title, once again, is On Being Ultimately Composed of Simple. So what do I mean by composed? What do we mean? Since this is a conference on the metaphysics of composition, we all have views, of course, but I need to be precise about how I will be using the term, and I will be using it in the way in which most mereologists use it today. Namely, the following, that X, and I use my variables to range over individuals, not pluralities. X is composed of the phi's, where phi is any formula that may or may not be satisfied, but in this case it will be. That means simply that X is a sum, a mereological sum or fusion of the phi's, and that the phi's are pairwise disjoint, i.e. they don't have any parts in common. What do I mean by a sum or fusion? There are many definitions. I'm sure some of you are familiar with the rich debate on how to actually capture this notion of a sum or a fusion. The notion that I'm going to be using, and in fact the other notions would grant exactly the same result that I'm going to present today, but the one I'm going to be using is the one that goes back to Lesniewski, and actually more precisely to Tarski's, let's say, non-standard presentation of Lesniewski's view, i.e. A presentation within the language of classical first-order logic, which is the following. X is the sum of the phi's, means simply that each of the phi's, each of the things that satisfy that formula is part of X, first, and secondly, every part of X overlaps, i.e. has some part in common with at least one of the phi's. Okay? Formally, that's captured by this conjunction. Secondly, what do I mean by a simple? Well, I mean a mereological atom. So X is a simple, simply means that X has no proper parts, regardless of X's shape, size, and so on. So this is really the general notion of an atom that we inherited from Democritus, so to speak. So don't think of atoms or simples as being point-like. They may be extended. They may have various other properties. The interesting and defining feature is that they have no proper parts. Where by a proper part, I simply mean a part that's distinct from the whole. Now, whole with a W, of course. So X is a proper part of Y, means X is part of Y and distinct from X. Now, the central notion then here is the notion the relational predicate part of. That's why I said this would be within the framework of mereology. I'm sure you're all familiar with it. I'm going to be thinking of it as a relation that's reflexive, anti-symmetric, and transitive. For simplicity, take it or leave it. We can discuss the relevance of this if you want eventually, but I don't think it matters much. I'm not going to be needing much more than that. So weak supplementation, which is a principle that is interesting but controversial, will at some point perhaps feature in this discussion. But just think of it as a simple partial order for now, nothing more than that. So I'm going to use A for being an atom or a simple, which means, again, no proper parts, and PP is defined as I said, okay? So that's the basic vocabulary I'm going to be working with. So here's a brief map of the theoretical options we have when we start thinking about such notions. Are there any simples? Are there any mereological atoms? And of course, I'm going to be perfectly dualistic here, so you can say yes or you can say no. No other option admitted, or at least contemplated. If you say no, then that means that you think everything is gunk. So this is the position of infinite divisibility. And you add your little axiom that says there are no atoms. Everything is not an atom. Okay. Good. If you say, oh, by the way, which doesn't mean that you're going to capture exactly the models that people have in mind when they believe in gunk and so on. More work needs to be done, but it doesn't matter. I'm not going to focus on this branch. I'm going to focus on the other, where you say yes. If you say yes, you have a further question, which is, are there just simples? Or are there also composite entities? And if you say yes, then you're a nihilist. Okay? There is no composition. There are no composite objects, say tables. There are simples arranged table-wise, to use a famous way of putting it. There are no human bodies. There are simples arranged human body-wise and so on. So everything is an atom, nothing else. This is Democritus, in a way. Democritus said just atoms and void. Well, almost like Democritus. If you say no, then you're, say, with the majority, and your further question is, okay, fine, there are simples, but is everything composed of simples in the sense I've described? But also, if you want, in a more pre-analytical sense of being made up of, composed of in some general sense. And again, you've got two options here, yes and no. If you say no, then fine, just tell me more at this point. So at this point, you believe that there are simples, but you deny that everything is made up of simples. Here's an interesting story they're going to tell me. That's not my story. It's your story. My story is on the left again, and it comes with the answer in the affirmative, yes. If you say yes, everything is composed of simples, then you believe in some form of atomism. And given the definition I gave, that really is usually captured by this axiom. For every x, there is a y, which is an atom, and that's part of X. In other words, everything has atomic parts. So I'm going to focus on this view and on this way of capturing it, the axiom that you see there. And the reason is that this axiom has a long history and has recently been attacked in various ways. So I want to convince you that this is the right way to capture atomism, even though in the second part I will then show that there are some additional, more hidden worries that the atomist has to face. So let's focus on this. It's usually called atomicity. So for example, most of us have started reading books such as Peter Simon's book on parts, or even before that, the 1970 book by Rolf Eberle called Nominalistic Systems. Those are the first systematic attempts to present a variety of mereological theories. But even earlier, if you go back to papers published in the Notre Dame Journal of Formal Logic by the Polish mereologists in the 50s and the 60s, and then eventually by some American mereologists such as John Clay, all of these people, all of these books, they all present atomicity this way. But there are objections. In particular, one objection that I find particularly interesting is this one. The axiom rules out gunky worlds, that's for sure, because it says that everything has atoms. So, of course, there are atoms, and therefore, since we're assuming the domain to be non-empty, the existential quantifier is non-empty, and therefore, we're not in the realm of infinite divisibility across the board. However, the objection goes, this axiom fails to capture the atomistic intuition to the effect that everything is made of atoms, because it doesn't quite say what the atomistic intuition says. Namely, it doesn't quite say that everything is composed of atoms. What it says is that everything has atoms, i.e. atomic parts. And there is, at least prima facie, a big distinction here. So since this is a conference on the metaphysics of composition, I'm actually going to talk more about the formal structure of this notion as opposed to the underlying metaphysics, but I hope the connection is close enough. So here is one way to show that this worry is prima facie serious. There are models of this axiom, models of atomicity, together with the partial order axioms that I mentioned earlier, that allow for infinite descending proper parthood chains. Some of you may be familiar with this. The first model of this sort actually was mentioned by Rolf Eberle in the book that I mentioned earlier. Eventually there has been some discussion. Aaron Kotmar talks about this sort of model in his paper on atomicity that came out in 2013. And Anthony Shiver published a paper more recently in Field Studies objecting explicitly to this way of capturing atomicity on the basis of models of this sort. So what do these models look like? Here's a very simple example. It's an infinite descending, as I said, chain of the proper power relation. The dots are entities in this model. The lines, of course, going upwards are the proper power relation. So X has an atom on the left, and then something else, Y, which is a composite object. It, in turn, has an atom as a proper part on the left, but it also has another composite part, Z, on the right. And Z, in turn, is organized the same way, and so on and so forth. Okay? So it keeps going down that way. So obviously the axiom is satisfied, because for every X, and here I'm sorry that I used X, Y, Z, I should have used A, B, C in the diagram, but anyway, for every entity in the domain, either it's an atom, if you find it on the left, in which case, of course, it has a part which is an atom, namely itself, given that parthood is reflexive, or else it has a proper part, which is an atom, even though it also has a proper part which is a composite, and that has further proper parts. So here's a simple way of describing why this is unpleasant, because here the pattern of decomposition that goes down the right branch never bottoms out, keeps going, looking awfully similar to a gunky precipice. We're supposed to rule out gunk, but it looks like this is very similar to gunk. Here's a concrete example if you want to be precise. Just think of X as the set of all natural numbers, and then you start removing numbers on the left, so to speak. First you remove the number the number 0, and you're left with the rest, Y. Then you remove the number 1, and you're left with the other numbers, and so on and so forth. Obviously, this is never going to bottom out. Okay? And here, of course, parthood is interpreted as just set inclusion. So models of this kind of being regarded as problematic. So here's what I'm going to say. I'm going to say two things. First of all, I'm going to say that we should not worry. Models of this sort are in fact atomistic, everything is indeed composed of atoms. And in fact, it's enough to look at the picture again. If indeed it goes on forever, just look at the theoretic model that I illustrate here on the right. Everything is composed of atoms, namely natural numbers. The question is that it is one thing to say that everything is composed of, quite another, as I shall emphasize in a second, to say that you can decompose it into its atoms. Cheever says this. He says, even though it is true that everything in this model, M, is either an atom or has an atom as a proper part, it is also true that every composite has a composite as a proper part. But if every composite has a composite proper part, and this is the part that I object to, then it is false that everything is ultimately composed of atoms. It is, at least partly, composites all the way down. Hence, M is not atomistic, even though it satisfies the axiom. So I object to the second part. I object to the claim that if every composite has a composite proper part, then it's false that everything is ultimately composed of atoms. In fact, Aaron Cotnoir, in a paper that came out before this one, said what I think is correct. He says that in a model like this, of course I have to add some square brackets because it wasn't talking about this model, but something of that sort. Well, this is a model of classical atomistic mereology in which the proper partial relation is non-well-founded. That's the peculiarity of this model, i.e. it's infinitely descending. Ganki worlds are not the only ones that have this feature, namely that a proper partial relation is not well-funded. But we shouldn't confuse being non-well-funded with violating atomicity, which is to say, we shouldn't identify being non-well-funded with being Ganki. That's an important distinction. Models of this sort do not violate the idea that everything is ultimately composed of atoms. They violate the idea that everything can be decomposed into its ultimate constituents. Now, that's an important distinction. I think we should think about it because a lot of contemporary philosophy is focused on the special composition question. And the last time I saw Peter Van Inwagen, I told him, look, when are you going to write about the special decomposition question? Because it doesn't mean that you can simply look at the same question from the other side. There are different issues here. And in particular, I believe there's a subtle trade-off between metaphysical and epistemological issues here when we go from composition to decomposition. And if you look at the history of the debate on infinite divisibility, you will see, especially in early modern philosophy, that the trade-off and sometimes the confusion between metaphysical and epistemological issues is responsible for the way in which the debate developed. And I think we should be aware of this when we talk about, even today in this kind of simplified formal settings, when we talk about these things. So that's problematic, the fact that you cannot decompose things into their ultimate constituents. It's problematic only if, well, I should say if, but especially only if atomism is meant to carry the weight of metaphysical grounding. If that's what you're after, then of course this is a problem, because then the atomist ontology seems to drain away down a bottomless pit, as Jonathan Sheffer put it. Or, to use another phrase of his, being is infinitely deferred, never achieved, precisely because you never get down to the bottom. But a simple way to think of a model of this kind is just take the line, the real line, and for the sake of the argument, let's agree that lines are made of points. Of course, there is a long history also about this puzzle. How can something extended be made of unextended parts? Never mind that. Let's just buy a standard set theoretic geometry. Lines are sets of points. So the real line is a set of points. Of course, it's uncountable. Obviously, you will never be able to decompose it into the points, but that doesn't mean that it is not composed of points. So we should be very careful here. And that's the first message that I want to offer. In fact, here you might want to look for a way to characterize the difference between those models that are well-funded and those that are not within the atomistic picture. Superatomicity would be a good option. Given an object X, our axiom atomicity guarantees the existence of some Parhut chain that bottoms out at an atom, namely the one on the left. Superatomicity, which is Aaron Kotnor's proposal, would require that every Parhut chain of X bottoms out, a property that obviously fails in M. So if you can capture this way of ruling out undesired models, then you will probably be happy even if you focus on decomposition and not just composition. The trouble is that it's not quite easy to formulate this requirement in a standard first-order language. However, that we can do something of that sort comes from the fact that in algebra, in Boolean algebra, this notion is well known. So, for example, the standard definition that goes back to Mostovsky and Tarski says that a Boolean algebra is superatomic if and only if every subalgebra is atomic. For example, the algebra generated by the finite subsets of a given set. Now, since we know that there is an important relationship between models of mereology and Boolean algebras, we can piggyback on this kind of result to capture it, but it's not easy. Anyway, so that's the first point. Second point. Although atomicity, the axiom, does not say that everything is ultimately composed of atoms, and I agree with that, it implies it. That's what axioms often do. They imply, they have theorems, they justify other claims. So here's the axiom, atomicity. Everything is composed of atoms. How are we going to say that? Well, let's put some question marks to begin with, and let's fill in the details step by step. I said X is composed of the phi's means that X is the sum of the phi's, and the phi's are pairwise disjoint. That's a standard definition. All right, so in particular, then, to say that something is composed of atoms, so here the phi's are X's atoms, is to say that it is composed of its own atoms. What's the thing jumping down there? That's my family trying to reach me. Oh, it's okay. To say that something is composed of atoms, then, is to say that it is composed of its own atoms. So X is composed of atoms means that it is a sum of X's atoms, and that all of X's atoms are pairwise disjoint. I'm just instantiating the phi in terms of being atoms. Now, of course, all atoms are pairwise disjoint. They have no proper parts, so they cannot overlap. Either they're identical or they are disjoint. So the second conjunct is redundant. So really, X is composed of atoms simply means that X is a sum, a mereological sum of its own atoms. X is the sum of the phi's, we said, is each of the phi's is part of X, first, and secondly, every part of X overlaps at least one of the phi's. So let's fill that in with the relevant value of phi. We get that X is composed of atoms, means that each of X's atoms is part of X, first, and second, every part of X overlaps at least one of X's atoms. Now, this is in the right language. We can finally put a formula that says that. There it is. It simply says for every y, if y is an atomic part of X, then it's part of X, and etc. So that's just the symbolization. So let's put it up there. That's our sentence, our claim. So atomicity doesn't say this. I claim it implies it, and I'm just going to show it because I want to make sure that you're convinced. So first of all, the first conjunct of this is a logical truth, since the consequent is one of the two conjuncts of the antecedent, pyx. So we can just drop it. Gets down to that. Now, since an atom is overlapped by something, Z, if and only if it is part of Z, given that it has no proper part, this is assuming reflexivity. Then, of course, this can be simplified by replacing the overlap relation with just Parhut. So there it is. Now, for any Z, atomicity, our axiom implies this. Since the axiom is a universal claim, I instantiate it with Z. You see that? So the X has been instantiated by Z. So in particular, for any x, we can plug in the antecedent pzx. That's a logical move, kind of a trick, but we can certainly do that. Given any sentence, it is the conditional with any antecedent holds, if that holds. Using transitivity, we can add pyx in the consequent, because if y is part of z, which is what the second conjunct says in 2, but z in turn is part of x, which is what the antecedent says, then y is part of x. We turn around the two, the second and third conjuncts in number 3, and we get number 4. So we switch pyz and pyx, we get pyx and pyz. Useless move, but the reason why I do that is because that's exactly what we have up there. And so we have the implication. And of course, since this was for any z and for any x, we get also the universal closure. So there it is. Atomicity doesn't say it, but it does actually imply. So if everything has atomic parts, then everything is ultimately composed of atoms or simples. And that's the thing. So I would like you to get rid of this kind of worries. It's good that for many, many, many years we've been using this axiom, because it does, in fact, do what it's supposed to do. Of course, there are issues because atomistic models may not be well funded. That's fine. That's an interesting thing. It's a different preoccupation. It's a preoccupation about decomposition as opposed to about composition, etc. So that's my first message. Okay, I guess we can skip this. This is about it. So the moral is, if we take composition to mean what it usually means, the objection misfires. Unfortunately, and here comes my second message, there is a much worse scenario. There are pretty standard meteorological models in which everything qualifies as composed of atoms, composed of simples according to our definition, and yet some elements in the domain are gunky, which is to say they're not really made up of atoms in any obvious sense. And this second part of my talk is actually based on joint work with Xin-Chen Tsai, and we do have a paper that describes this kind of models. It's actually a very short and highly dense paper, so I thought it wouldn't be a bad idea to go through the main idea. The reason why I'm going to do this is that I am actually sympathizing with atomism in many ways and for many reasons, including the good old reasons that Democritus gave us. And so I am worried. I'm not worried by the first part of the story. I'm worried about the second part. So what I'm going to do now, and you have to be patient a bit, is I'm going to walk you through the construction of one model that is similar to the one that was published in this paper that came out in Erkenntnis. And this is a model that has this funny feature, that everything is composed of atoms and yet has gunky parts. That's kind of hard to make sense of. So the way I'm going to ask you to walk with me through this is to imagine, just focus on an open interval, G, non-empty, on the real line, R, and then just take A to be a countably infinite set of points on R, disjoint from G. So for the sake of concreteness or definiteness, let's think of G as the open interval 0, 1. Okay, so all the real numbers between 0 and 1, but excluding the two endpoints. And let's take A to be the set of all natural numbers. So in particular, those will include the two endpoints of the open interval. Is that clear? So we take that interval plus all the natural numbers. Okay? Now I'm going to construct a model where our domain will include a bunch of things which are composed of parts of G and a bunch of natural numbers, so that everything will include, the interval G is obviously gunky, so everything will include a gunky part together with a bunch of atoms, and in such a way that atomicity is satisfied. Is that clear? So now it's going to be a little tricky. I'm going to do it as follows. So we want, of course, to add the mereology now, because don't think of the mereology as coming for free with set theory. We have to actually construct now the parts. That's, again, the kind of useful exercise that we have to engage when it comes to this matter. So I'm going to do it as follows. I'm going to cut these things into, namely G and A, into progressive halves. First of all, I'm going to define a function, two functions, alpha and beta. Think of them as left and right, if you like, alpha and beta, which are going to split every open interval, every open subinterval of G, so every open subinterval in our concrete example of 0, 1, into, let's say, the left half from x, i.e. 0, to the midpoint, and into its right half from the midpoint to y, i.e. 1. Is that clear? So intuitively, left and right, that I said. So here's a concrete application of this. You start from G, then you apply alpha and beta, and you get the two halves from 0 to 1 half, and from 1 half to 1. Then those, in turn, will be subjected to this kind of splitting, and you get alpha of alpha G from 0 to 1/4, and beta of alpha G, i.e. from 1/4 to 1 half or 2/4, and so on and so forth. Is that clear? Good. Now we're going to do the same, or roughly the same, with the natural numbers. The natural numbers, of course, are ordered in a natural way, if I can say so. So I'm going to split them using a function, with the help of a function that basically assigns to any set of natural numbers in their order oddity or evenness, depending on whether they occur at an odd place or at an even place in that sequence. Okay, so obviously, if we have all the natural numbers, then 2, 4, 6, 8, etc. will be the even ones, and the others will be the odd ones. But if you drop a few of them, then of course you get a different classification. So if you do it that way, basically you split, you take always the odd on the one hand and the even on the other, and you get a similar splitting. Here is a concrete example. We start with all the natural numbers on the left, the even, on the right, the odd, and then we start splitting the even, and we take the even ordered ones, 0, 4, 8, versus the odd number ones, 2, 6, 10, etc. Okay, so it's just a progressive splitting. I hope that's clear enough. Once we have this, third step, we're going to build our domain. We take a bunch of sets. The first is the set that takes G together, i.e. the interval together with all the natural numbers. And then we take the next step, two sets, namely, remember the splitting. We take the ones that we get by splitting on the left and the ones that we get by splitting on the right, and so on and so forth. Eventually, since time is short, this will give us a sequence of domains such that after the first one, which is just a G union A, each domain will contain exactly two, each D sub k plus 1 will contain exactly two to the k plus 1 elements, half of which will be, so to speak, taken from the left, and half of which will be taken from the right. Here's an example, a picture of the beginning of the sequence. So D0, as I said, is the whole thing, the union plus the interval plus the set of natural numbers. D1 will take the first semi-interval together with the even numbers, that's the first element, and the second semi-interval together with the odd numbers, and so on and so forth. So the picture is roughly this. So D0 is the interval plus all the numbers, and then you start splitting the interval and taking half of the numbers and half of the numbers. Is that clear? So if you think of these as actual objects, spatial, as it were, objects, that's exactly what these domains look like. And now we construct a model by taking the union of the domains. Sorry, this I just explained. Oh no, here we go. We construct a model by taking as a domain the union of all of these D's, together with all the atoms. The atoms are what? The singletons of the natural numbers. So singleton of natural numbers provide atoms or simples. The union of all those domains will give us all the other elements, and we interpret, of course, parthood as inclusion, given that that's a set theoretic model. I hope that's clear. Well, if it isn't, I can explain the details again later. Let me try to draw the moral now, because here is what this model does. So these are two important properties of this model. The first is that, on the one hand, every element in our domain, constructed as I have, has atomic parts. And the picture with the segments and the dots should show that you always have some dots. You always have a little segment, gets smaller and smaller the segments, fewer and fewer the dots, but you always have some dots and you always have a segment. Okay? So it satisfies the atomicity axiom. On the other hand, every non-atomic element, i.e. every composite element, can be divided indefinitely into proper parts, which are, it depends on whether you take alpha or beta, left or right, but which are always unions of a bit of a segment and a bunch of atoms, points, simples. So every element in the model, every composite element, not the atoms, but every other element, in addition to having atomic parts and therefore satisfying atomicity, it also has gunky parts. Not only does their pattern of decomposition fail to bottom up the atoms, as with the original case that I discussed in part 1, the atoms are just not enough to generate them. So they are not, in some intuitive, obvious, prima facie sense, composed of. They're not generated from the atoms, because we always have this bit that comes from the interval, and the interval is not analyzed mereologically in terms of the points that make it up. And that's a disturbing or unpleasant fact. Now, my moral here, and this was also how Tsai and I put it in our paper, but here I'm going to add in conclusion a couple of things. My moral is that what happens here is that it's really our understanding of composition that is in trouble, as opposed to saying that the atomist is in trouble. And I think this is important, because we've been working with that notion of composition in terms of sums, at least since Peter Van Inwagen asked the spatial composition question. That's the notion of composed of that we've been working with, and it just seems to be in trouble. On the one hand, by the first fact, every element qualifies as composed of atoms according to the definition, via the argument that I gave earlier. On the other hand, by the second fact, the non-atomic elements are not really composed of atoms, since the atoms in the domain are not enough to generate them. Now, getting to a conclusion, perhaps the culprit here is, as always, or as often, is the relevant notion of sum, mereological sum, which I used which Peter Van Inwagen used to define the relevant notion of composition. But I don't think that's true. In fact, I constructed the same story using all other available notion of mereological sum, and the argument goes through. So it doesn't, for once, it's not that problem. I think a better question to ask for us, especially in this context, is what sort of mereology is needed to block the problem, to block this kind of case, where there is a clear gap between our understanding of composition and what the theory does. Now, very quickly, notice that the model satisfies strong supplementation. If x is not part of y, then x always has a part disjoint from y, which is to say, I skipped the proof, which means that the model is extensional. So it's not a weird model, it's an extensional model. Whether or not you like extensionality, surely you don't want to rule out extensional models. This is a good feature. So it's a very obvious kind of model in that respect. That means, however, that extensional mereology is not strong enough to block the problem. So we need something stronger than extensional mereology to get rid of it. Notice that the model does not satisfy, by contrast, unrestricted composition or mereological universalism. It is not true that given any bunch of phi's, there is always something that is the sum of them. For instance, given any 2 points, A1, A2, you have the atoms, but you don't have their sum. That's not an element of the domain. In the domain, everything is the union of a bit of that interval and a bunch of atoms. You don't have just unions of atoms. So it's clearly not closed under unrestricted composition. So general extensional mereology is, which is closed under strong composition, is strong enough to do the job. But of course, anything in between, that's an interesting question. Extensional mereology is too weak. General mereology closed under unrestricted composition is strong, but sounds like it's a bit too strong. Anything in between. Now, I'm going to skip these bits here about other options in between that I can go through. The moral is, what is clear is that some principle, well, I wrote it twice, well, just once, some principle governing mereological summation is needed to block the problem. Either unrestricted composition, in fact, the example that I'm skipping because of lack of time shows that finitary composition is not enough. So some principle is needed to block the problem. Some kind of composition principle is needed to rule out these unintended models and therefore to restore the intended meaning of composed of. That's the moral of this. But that is like putting the cart in front of the horses. We simply cannot assume a principle of composition to make sense of composition. The whole problem here is with the notion of composition, and we're saying, oh, we need a principle of composition, maybe unrestricted composition. No, hopefully something weaker than that. But we're supposed to use the notion of composition to then see whether, say, unrestricted composition is true as opposed to some kind of restricted composition. So I really think we are in trouble. Surely we cannot assume a principle of composition to make sense of the special composition question. So I'm going to stop here, mostly because I think that's it. Namely, I'm going to stop with the moral to the effect that we have to rethink the notion of composition itself, or else live with this model. Now, this is a conference on the metaphysics of composition, so we are doing this. My hope is that in addition to substantive metaphysical aspects of the metaphysics of composition, we keep in mind that there are some issues lurking in the background when it comes to keeping under control our understanding of the models of what we say, because this is not Löwenheim-Skolem kind of problem. No, this is a very simple model, extensional, and it causes troubles. And I stop here. Thank you.
Thank you very much.